Hi everyone, this is going to be a dry lab version of the lab that we missed today. It's called Enthalpy of Phase Changes. Enthalpy is just a word for heat, and phase changes involve going between states of matter. So that's what this lab's going to look at. So what we're going to go through is first we'll talk about the theory, the role of energy in changing states of matter. And then I'll talk about the two experiments that we would have done. And then you'll process some data on it, some sample data. And then there'll be some follow-up questions to do. So the change of state that is pretty familiar to most people is melting. So let's pretend that we have a beaker of ice and we want to melt it. If you want to melt ice, you have to heat it up. Heat needs to go into the ice in order to melt it. If we put a thermometer in here and we measure the temperature as we heat this ice up, what we would predict is that the temperature increases as we continue to heat the ice as it melts. But this is not what actually happens. So on the next slide, you're going to see a version of this graph where there is actual data where I took a beaker of ice and melted it and measured the temperature as it did so. So what we've got here is this pretty long plateau where the temperature doesn't change even though the ice itself was being heated. It was sitting on a hot plate. Eventually, the temperature does increase, but the focus here is this sort of plateau. Why is this bizarre plateau here where we're heating the ice, but the temperature is not changing? That's sort of strange. So to understand why this is happening, what this energy is doing, we have to think about how the particles are arranged differently in the three states of matter. So we know that solids, liquids, and gases have different characteristic properties. Solids have a fixed shape, and they also have a fixed volume. Liquids have a fixed volume, but their shape can change. And then finally, gases have neither. You can take gases and make them bigger and smaller, and in doing so, you also change their shape. So we can explain why they have these different properties if we think about how the particles are arranged down on the atomic scale. So on the atomic scale, solid particles are set up in a way that the particles themselves are fixed in space. They can't move past each other, and they're very close together. In the liquid, they're still pretty close together. Liquids and solids have pretty similar densities, which implies that the particles are similarly spaced. However, we know that liquids can pour, and what that's implying is that those particles have some freedom of movement. They can sort of tumble past each other. So the particles in a liquid are sticking to each other, but they're not held in place. So in order to go from a solid to a liquid, you have to break them up a little bit. When you have a gas, the particles are totally separate from each other, and they're pretty far apart relative to their size. Today, we're going to look at changing states going in a particular direction, going from a solid to a liquid, and then also going from a liquid to a gas. In order to make these happen, energy must go into the substance for these to occur. For water, there's a certain amount of energy that's required to melt it, and a certain amount of energy that's required to boil it. So the numbers you're going to see in just a second are measured values. The heat of fusion is the amount of heat required to melt ice, to turn the ice into a liquid, the heat required to melt it. So the measured value for this is 334 joules. The positive sign is telling us that the energy must be absorbed in order for that to happen. Energy has to go into the ice to make that happen. In order to turn liquid water into gas, i.e. steam, the amount of heat required to do that is called heat of vaporization. Vaporization is just a fancy word for boiling. To vaporize something means to turn it into a gas. The measured value for this is 2,370 joules. Now, these amounts of energy depend on the quantity that you're using. So these actually include a gram in it. So these numbers are saying that the amount of energy needed to turn 1 gram of ice into 1 gram of water is going to require this many joules. And then the energy required to turn 1 gram of water into 1 gram of steam is going to require 2,370 joules. So we have to include the amount there. Now, these two numbers are for the same exact amount, 1 gram, but there is a significant difference between the two. This number is is about 7 times higher than this number right here. And if we think back to the particle arrangements, that makes sense because in the solid and the liquid state, solids and liquids are pretty closely related to each other, meaning the particles are very close together. They're still sticking to each other. But when you go from a liquid to a gas, you have to totally pull all these particles apart from each other. And that requires a lot of energy to do that. So that explains why it takes about 7 times more energy to turn liquid water into gas than it does to turn solid ice into liquid water. All right, so that's the background. The two experiments we were going to carry out today are going to involve determining the heat of fusion, that's melting, of ice, and then determining the heat of vaporization of water. So for the first part, to determine the heat of fusion for ice, what we were going to do is carry this out in a calorimeter. That's just a styrofoam cup. So the way we can do this is we first have to measure the mass of the cup, put in some water, mass it again, put a thermometer probe in, and then have the LabQuest measure temperature over time. So initially, with water just sitting in this cup, the temperature doesn't change very much. So that's what this plateau is showing. After a certain amount of time, we dump in some ice, and as we'd expect, the temperature is going to go down and bottom out and then start to go back up. From this graph, we can get the highest temperature, the max, and the lowest temperature, the min. And what that allows us to do is to calculate the changes in temperature. Finally, the last piece of data that we need is we need to know how much ice is in there, and we can weigh it. We can determine the mass of the ice. So in order to determine the heat of fusion, we have to make a series of assumptions about the flow of heat. The first assumption is if we're looking inside this cup right here with water inside, we have to assume that the cup is a perfect insulator. So that means that no heat goes in and no heat goes out. It's a perfect insulator. Again, it's an assumption. It's not true, but it keeps the calculations pretty simple. So that means that if there is heat flow inside, it's totally contained. So the water in the cup are at higher temperatures than the ice. So that means that the heat is going to flow from the water into the ice and from the cup into the ice too. When we're looking at heat flow, we need to specify where the heat is going. So we need a point A and a point B. So there's two terms that apply to that. The part of this that we're focusing in on is called the system. And then the other two, the water and the cup, those are called the surroundings. And in this situation, the heat is going from the surroundings and into the system. And we would call this process endothermic. We can use an equation to calculate the heat that the water and the cup are going to lose. So this is calculated, heat is Q, by taking the mass, multiplying it by the specific heat, which is a constant, and then multiplying it by the change in temperature, which we can get from the LabQuest. So here are some sample values that are going to show you the sequence of the calculations. So let's say you use this equation here to calculate the amount of heat that the water loses, and you get negative 800. The negative just means that it's losing the heat energy. Then you do the same thing for the cup, and let's say that the cup itself is losing negative 50 joules of heat. And because these are both what we're calling the surroundings, we can combine these numbers together. So negative 800, negative 50 is negative 850. And then another assumption we're going to make is that if this is losing 850, we're going to assume that the ice is gaining all of it. So there's a step in the calculations where you're just going to take the number and flip the sign around. So if this is losing 850, from the perspective of the ice, it's going to gain 850, and that's shown with this positive sign right here. So there is a spreadsheet that you'll get a link to that will have some sample data on it. So it's going to look like this. There'll be a box up top that will show you some general tips. There'll be some sample data in here. And then the other thing you should be able to see are these equations right here. These are going to be helpful in doing these calculations. So I would recommend opening this up in Excel rather than Google Sheets because the equations won't show up. So let's jump to the spreadsheet. There we go. All right, so Excel can do calculations. Yeah, I don't know how much experience you have, but it's very handy to learn how to do this. So let's say we want to find the calculated mass of water. What you do is if you want Excel to do a calculation for you, you start with typing equals, And if we want to get the mass of water, what we're going to take is this number minus this number. So all you have to do is you don't even have to type in the number. You just have to click on it. So that minus that. And so what you see here is the address of the cells. The letter is the column, and then the number is the row. So you click on those, you hit enter, and voila, we have the calculation. So you proceed down and you do these calculations. And what I would recommend, again, is do this right on Excel because they all depend on each other. And if one changes, it changes the others. So if you end up realizing that one of these numbers is messed up, you can fix it, and then Excel will just redo the calculations all on its own. So that's pretty handy. Okay, so that is the data to process for the first experiment. Let's talk about the second experiment. So the second experiment is to determine the enthalpy of vaporization, the amount of heat required to turn a liquid into a gas. The way we would carry this out is taking a graduated cylinder, filling it up with water almost all the way, and flipping it upside down in a water bath. So what we have here is an air pocket, and that's the focus of this experiment right here. We would put it on a hot plate and warm this air pocket up in the water bath. And as gases warm up, they expand. So this air pocket's going to get bigger and bigger and bigger. And then once it gets as big as it can be, we are going to put a thermometer probe in there and measure the temperature as it cools off. So what we can now get as this cools off, if this is now off the heat, is we can measure the volume and the temperature. So we get that set of readings. We let it cool off a little bit more. The air pocket shrinks, and we take another set of readings of volume and temperature, and we continue this process. So what we're accumulating is a series of readings of temperature and volume of the air pocket. Then what we can do is use the ideal gas law and turn these volumes into pressures. And what we'll have is a series of readings of temperatures and pressures. So we have this table of pressure and temperature. So then the question is, well, how do we turn these into the heat of vaporization? There's an equation that relates these three items to each other. Sorry about that. Okay, so we have pressure, we have heat of vaporization, and we have temperature. In order to get them to work in an equation together, we have to do a little bit more math. So we're not going to walk through how this equation was derived, but just suffice it to say that this is how we can relate these three things together. So in order to get an equation that relates these three, what we have to do is take the natural logarithm of the pressure. We have to take the temperature and put it on the denominator and have 1 on the top. And when we do that, we get an equation that looks like this. So what we've got in here is a negative sign. We have divided by, and we have R. That's the gas constant. This equation is in a form that might look familiar. It's in the form of y equals mx plus b. That part of the equation we don't need to consider. So all we need to consider is that this equation is in this form. What we can do with it is we can graph the natural log of the pressures on the y-axis. We can graph 1 over the temperature on the x-axis, and then we can get the slope. From the slope, we can calculate the heat of vaporization. So this equation is just going to be a tool to get us the heat of vaporization. So on the graph, we're going to put 1 over the temperature, natural log of the pressure, and we're going to get a straight line. The line's going to go down, so that means that the slope is going to be a negative number. And from the slope, which we can have a spreadsheet tell us, we can determine the heat of vaporization given this constant right here. So we're going to use a spreadsheet to make the graph, tell us the slope, and then we can use the gas constant and the value of the slope to calculate the value of the heat of vaporization.